Single strand double one, it doesn't work. The closest I got is using 3 strands. The closest like 16 inch. What's possible?
Sudah dekat pintu.
One strand.
Bye bye.
Wait, can I borrow your paper? Horsepower 8. 8 before.
Oh, Luis, kalau punya pakai 2,6 masih kegedean 15,8. Jadi salah. 26.
Center to center.
Kita harus desain musik.
Iya, gua pakai 50, 6 strand. Gua pas ngeliat kan, gua dikasih garisnya.
Terus tuh dia main-mainin.
Ya, dia tangan 50. Gua pakai 50.
Terus ini kan,
Kalau di garis boleh
kalau nggak salah dapat 35 gitu.
Gua di garis.
Garis apa?
Misi.
Aku juga nyampe sana. Gue itu mulu. Ngentotnya gitu.
Okay, some old boys. So Mr. name, Brian Aurelio.
Ini gimana bisa
Mikael Luis. Arif Pramana.
Di kelas 3 SM5 itu.
Matthew Tambian.
Supaya dapat ekspedisi
Nicholas Julius. This is
Kita remedial.
yeah.
Gue satu.
Right. Nathanael. Brian Aurelio. Tadi. Rayfan. Okay, Michael B. Mikael Luis.
Jim yang kemarin. Gue coba satu-satu lagi dari 2, 3, 4, 5 masih gak nyampe-nyampe baru sampai gue nulis di atas sempat nulis nama.
Geser dikit lah.
Tadi pesan gue udah yang lain aja. Soalnya
Amelia Edward Nicholas Edward Matthew Tandian no. Jason Alexander Brian Aurelio Richard Rayfan Adel Reko Aska
iya gue lupa.
Aska Aiman Justin
Emang nggak ada, lu bisa sih. Tabut
Wempi
Power bagi
3 cents ounces I got. Mine's like 66, right?
Yeah, I got 6.
I was asking. Yeah, that's the closest I could get. How do you get 6 strands?
Nicholas Julius Madeline Arif Pramana Nathanael.
Salahnya cuma Rizky doang.
Mikael Cristiano. Angelica. Brilliant. Marcel.
No, he's using the brake. He doesn't take the higher one.
Nathanael.
Makanya bel seleksinya apa? Gue langsung isi, terus gue bilang ini tuh bel beres. Dia bisa tapi apa? Coba deh pakai. Bisa nggak? Enggak. Show that it's a part. No, it doesn't. Benchmark
Itu nilai itu. They got worse. They got worse.
For the final item later on, what would be the problem of the one?
There might be multiple choice and calculation communication. I think last time I had 50 multiple choice, like the pre-test, post-test, and like two calculation problems. One of these quiz. Yeah, I usually pick ones that you score the worst.
Udah diambil sih.
Coba dikenal dulu yang
Itu banyak yang salah deh. Iya enak makanya. Jarak ya.
Who wants to ask a question on the quiz? What are the most common mistakes you guys did? Hmm?
It's just calculating.
Okay.
So you calculate every, like last time we used to we have to use degree, but I use radian for the angle.
Okay. Anything you wanna ask? I mean, what's most confusing to me is usually when in a quiz, a lot of people, the average is bad, but then there are some who get like 90s. So the statistics is like all over the place, right?
Yeah.
I mean, statistics is supposed to be like this, but what we have is like that. So I don't know how to make sense of the. I guess, I mean, I have a few, I noticed the statistics, I have a few who get like 90s, 95, 98, and then everyone else. So, I don't know how to interpret that. Is it like, you guys didn't understand, or is it really just calculation problems? Like,
Calculation problem.
really? Like what types? Give me the types of errors you guys did.
Unit conversion. Yes.
Unit conversion.
Yeah.
Well, on the chain. I mean, we're doing the remedial today, right? Yeah. And I think I gave you exactly the same problem, right? Yeah.
I did worse.
Yes. I didn't give you exactly the same. What else? What other error types that you guys did? Hmm? Overconfidence. Okay.
All of us is confident in the first.
That's a different type of problem.
Sometimes we forgot to like change it to the SI. So we expected
Okay. But the belt is all in inches,
Yeah.
right? I think the chain also
Yeah.
is in inches, right? Okay, well. Okay, let's continue our. We're close to finishing here. I have springs, and then. Do you guys do Passer's quiz?
No, this
Okay. All right. Let's start on this last topic. It's a short one. Springs. Springs are also everywhere, right? I mean, you see it in your pen. You see it everywhere. Of course, the purpose of springs is not damping. Damping is a damper. Store energy, right? I mean, you wanna have some compliance, and other times you store energy. You see it in your cars, of course, for the suspension. So you provide some flexibility. You store or absorb energy. If you look at a helical spring, it's basically a wire being wound, right? It's wound and then it creates that shape, and so you have the compliance or the flexibility. So you press with the force, it deflects, but then it returns to its original strength. The basic spring force calculation the force of the spring is equal to K times, oh come on guys,
A times delta.
yeah, delta x. So the deflection times the K. So if you see a K of say 100 Newton per meter, means that you need 100 Newton to deflect it 1 meter. Well, of course, you don't deflect springs 1 meter. In essence, this is like 1 Newton per 0.1 Newton per millimeter. Well, that's tiny, I guess, right? So 1,000 Newton per meter, there is 1 Newton per millimeter, right? So you press 1 Newton, it goes in 1 millimeter. So you press 10 Newton, it goes in 1 centimeter. So it's very straightforward, very linear, very simple. You have different types of springs. This is the typical one you associate with springs, right? It's a linear spring, compression. But there is also extension spring. You pull out and it returns to the original length, which is compressed. This is a conical spring. The K is actually non-linear for this guy. So it gets hardened as you compress. So the K is not constant. A conical spring is more constant. But the other reason people do this is that you can collapse up to a very thin piece. Basically, it collapses on itself. So if you need compression all the way down, then you use this. While this one has a solid length, and then you can go no more. Torsion spring, you basically do the angular, right? This is an angular spring. When you see this, you girls, right? Your hair clips. So it opens in an angular way. Okay, that's your torsional spring. This is what you see in pickup trucks, maybe heavy load vehicles. It's a leaf spring. Okay, and so you hold this here, and this is where the force is. It's going to deflect this way. This and this or Belleville spring, air cushion, or sometimes the material also can provide this springiness. Okay, so you got all kinds. This is a torsion spring, even though it's shaped differently. You have two coils here, but it's essentially a torsion spring. Extension spring, right? Usually you have these features to kind of put it in place. This is a constant force spiral spring. So you basically have a long angular displacement, right? Watches uses this, right? You basically want it. So it's a long angular displacement spring. Kind of a torsion spring, but torsion spring usually only displays like a few degrees, not a full circle, right? So this one you can do full circle. These are just different clips. I know it's not a spring in essence, but I mean they function as fasteners many times. And remember, our topic is machine design, so these are elements you see in a typical machineries or linkages. You see this in hose clamps, by the way, right? If you ever work on cars, radiator hoses often uses spring clips. So you press it, get it out, and it clamps nicely. So we'll get into the calculation, but before we go there, let's look at just how springs are made. This is a big one, but okay.
FM mode. Line E mode.
Oh, it's just me. That's a huge one. So you square off the ends, you cut. There are different finishes at each end. You do heat treatment to relieve the pressure, the cold work that is done. Probably automotive springs. Quality check. That's good. All right. Let's look at a more comprehensive video, but this is old.
Spring is a flexible metal device that returns to its original shape or position after it's stretched, squeezed, or twisted. Springs were first used in clocks during the 16th century, and starting in the late 1800s, in chair seats and bedding. Today, springs pop up all over. They're crucial components of modern technology. Different types of springs include compression on the right and extension on the left. During use, these torsion springs will twist at one or both ends. Workers start with rolls of steel cord. The cord diameters range in size depending on the type of springs being made. A machine called a dereeler unwinds the roll, feeding it to a computer-guided forming machine. This forming machine forces the cord through a channel, shapes it into a coil, and then cuts it into segments. Small wheels and a metal shaft guide the cord into shape. These are torsion springs for use in the automotive industry, which relies heavily on a variety of springs. The average car, for example, has about 350 of them.
Looks kind of hypnotizing, isn't it?
A cone-shaped yellow sensor detects the correct angle of each spring. A good reading is required, so the machine can move the next spring forward through the channel to be formed. This machine can produce up to 2,000 springs per hour, depending on their size. Here, another larger forming machine creates extension springs that are nearly 16 centimeters long. A mechanical arm grabs the coil and chops it into segments after it's formed in a channel. As the coil emerges, another mechanical arm steadies it to prevent it from vibrating. This keeps the spring's tension constant, enabling the machine to produce at top speed. In slow motion, you can see how the machine grabs the coil's first ring and bends it to form a hook. This all takes place as the coil emerges from the channel. A vise then secures the last ring on the end of the coil, while another arm twists it to make the spring's other hook.
So it's making the hook for the attachment because it's an extension spring.
Slowed down, you see how two arms surround the coil being held in the vise. One arm then grabs the last ring, while the other arm twists it upward.
That's fast.
This machine makes compression springs, a model with tapered ends that's often used in seatbelts. A metal probe detects the correct length of the springs after they're formed. The machine has 4 rotary shafts, called cams. A computer ensures each spring has the desired specs. The springs are also heated to relax the metal. This gives them the ability to retain their shape after flexing. Another machine creates longer, thicker torsion springs. It shapes the cord into a coil with a shaft and then passes it over a tube to steady it. This ensures the spring will have the required tension. Springs can be as thin as human hair or as thick as a broom handle. Train wheels, for instance, include some of the industry's thickest compression springs. This machine makes another type of spring, often called wire forms. They're flexible steel cords curved or bent at an angle. These ones, shaped like a W, are used in ovens. Here, a worker places a spring into a machine that makes its hooks. He uses an adapter to avoid hurting his fingers. He places each one individually because specs for springs can vary by minute amounts. This company makes some springs with hooks made of 2 rings instead of 1. Clients order them this way because the hooks are more durable. Custom orders for springs can range from just a few to many thousand.
That's a boring job to have. Like, put the springs on the machine and let it bend.
This is another type of wire form. It'll be used in a firearm. A worker assembles it by hand because it's so intricate. After joining 2 base pieces, he places them into a small die. Using a foot pedal, he controls the die to bend the segments and complete the assembly. To check the compression spring's tension, a worker tests it with a weight gauge. The correct tension varies depending on what the client wants. A 3.8 centimeter long spring, for example, might need to withstand 5 pounds of tension when compressed to 2.5 centimeters. To test an extension spring, workers just add hooks to the weight gauge. Whether they're extension, compression, torsion, or wire form, and whether they're inside pens or satellites, springs prove that some old ideas definitely still work.
All right. So, it's just always interesting to see how it's made. I love these videos. Gives you insights on machineries as well. Now, what we're going to calculate today is how you get the spring constants based on the spring geometry. And in order to do that, you also have to understand how the ends affect what is called the number of active coils. The fact that a spring has 10 turns does not mean that all 10 turns is actively compliant, right? Because some of these are not effective. Now, this is the plain spring. When you simply cut it like that, now you can finish it differently because that's not useful. I mean, at least it's not as easy to use if it's plain end like this. So sometimes people do a squared and closed. Now, the way they do that, you notice that the last piece does not extend like that. But you see the gap is not constant here, right? So the gap is constant here, but here then it narrows in. So you take the end and then force it to be close to this one. So you have a flat here. So that's called a squared and closed end. This one is square. So they square it like that, and then they ground it. So they grind it. So you see it has a perfect flat, not just a round, somewhat flat, but it's totally flat. So this has a nice ground finish on that. This one, they simply just take this and then they just grind it, right? So they just grind it flat, and you see this is the ground marks. So based on these finishes, then you can determine the effectiveness of the coil. Okay, so I'll spare you the stresses calculation, but what you do need to understand is that who can give me a, well, that's too small to show. Okay, but anyways. So the linear spring, the compression spring, it compresses like this, but if I open this out into a wire, what's happening is actually I'm twisting the wire. Okay, I know it's hard to imagine. Maybe I can find some, thank you. Maybe I can find some animation on that later. But, so when you compress this, if I take this guy and just open it to the original wire that it was from, I'm actually twisting it. So when I compress it, what I'm doing is I'm doing this. I'm doing this to the wire. So therefore, the calculation is a shear stress calculation, not a normal stress, because I'm not bending it. The opposite happens in a torsion spring. So let's say you have a torsion spring like this, right? And so when you press on this, you actually twist the spring. But if I open this up into the original wire, you are actually bending it. I know it's the opposite, right? So if you compress a spring, you're actually twisting the wire. But when you bend, when you twist a torsion spring, you're actually bending the wire. Like this. This is bending, right? This is torsion. This is bending. Therefore, the calculation is a shear stress for a compression spring, but it's a normal stress, like a bending stress, for a torsion spring. So it's kind of opposite because you already form it in a different way. Now, skipping all that, this is the K, which is this K in your physics class, F equals Ks. Where do you get the K? This is where you get the K, from the spring construction. Small diameter, G. G is the shear modulus. Big D is this diameter. Notice that it's not the outer diameter. It's not the outer diameter. It's the nominal diameter, which is from the middle of that. So it's the outer diameter minus the wire diameter D. So notice this is not the same as this, right? So if this is the outer diameter DO, you take DO, you minus the radius, which is half of the wire diameter. This I'm calling this a wire because it is made from a wire, basically. Sometimes a very thick wire, but they call it a wire. So this is the wire diameter D, right? Therefore, DO, this D is DO minus D over 2 minus D over 2. Okay? Does everyone see that? Right? So if I want this capital D, which is the nominal diameter, at the center point of these wires, then it's DO minus D over 2 minus D over 2. Essentially, it's DO minus small d. Okay? That is an important feature. You're going to do this in the exercise. Any questions on that D? It's kind of small, but I hope you get that. This is the formulas for the different ends or the different types of spring ends. What is important, I guess the rest are not that important, but the total coil relationship with the active coil relationship is important. So if you have total coil of say 15, so let's say I have 15 turns, but it's a plane and ground. So this will be your total coil. NT is 15, but NT equals NA plus 1. Or in other words, my active coil is actually minus 1, which is 14. Okay? So my active coil is less than the number of turns to construct the spring. Okay, so if it's plain and ground, is Na plus 1, meaning that the Na is Nt minus 1 and minus 2 minus 2. Na is the number of active coils. These are the tensile strengths. So you look at the E and the G. For compression spring, you use G. For torsion spring, you use E. We'll do that exercise. Okay, so I'm taking this from the textbook. Again, I have to compress this material, so I get rid of some shear stress calculation. We'll just go to the K calculation because I think that's what's more practical. Okay, so a helical compression spring is made out of number 16 music wire, and number 16 is basically the gauge of the wire. I don't know whether you realize, but wires are measured in gauges. They are something related to the weight per length. Not the most practical way, in my opinion, but they do it this way traditionally. So it's a number 16 music wire, outside diameter. So DO is 11 millimeter. I think a lot of these catalogs are in inch, so we'll have to convert that. So MT is 12.5 turns. It's kind of cut off, but it's 12 and a half. Okay? Determine the scale, meaning the K, and the deflection will be caused by the load in part B, which was calculated before, but you know, ignore the deflection. We'll just focus on the K. All right, now from this table we can tell number 16. So this is the number of gauge. The smaller, the thicker, by the way. And if you buy a wire, by the way, electrical wires, say a 14 gauge wire. So 14, you will see, so this is non-ferrous sheet and all that, you know, they have different categories, and then you can find what the diameter is. In our case, it's a music wire, okay? And so number 16 is 0.37. So this is from table, is equal to 0.037 inch. Okay? So my K formula, D to the 4th G 8D to the 3 Na. So we're going to have to calculate some quantities and look up more quantities here. The G, let's look at the active coil first. Let's see, what was the finish? What was the finish? Ends are square. Okay? So, squared or close and squared and ground is the same. So basically, Na is 12.5 minus 2, so it's 10.5. And let's see, what else we need? We need G. So G is from the material properties table. Is the shear modulus. It's a music wire. Now we need the diameter, which is the wire diameter is 0.037. So we are here. between 0.033 to 0.063. Music wire, this one, the G is 81.7 GPa, gigapascals. So this is from table. Okay? Any questions? Then it's just math. So we have convert. Oh, wait, we need this D. Okay? So D is equal to D0 minus D over 2 minus D over 2. So 11 millimeters, convert that to H. Divide by 25.4. 0.433. Okay? So we have 0.433 minus 0.037 because this is D, right? We'll get 0.94.
0.037 kan pakai GPA, kenapa nggak dikecilnya yang jadi mili?
Right. Because I'm gonna end up using millimeters. Now I remember. So what is this in millimeters?
Times.
Huh?
Zero to conversion rate.
Yeah.
Si conversion itu complex.
25.4. So that will be 10.06 millimeters. Okay, now everything is metric, right? GPA is SI, and now we are consistent. Okay? Good catch. 0.94 to the fourth, 81.7 times 10 to the 9. 8 times 10.06 times 10.5. Now, after some conversion, you'll end up with 0.9 Newton per millimeter. This will get you to Newton per meter. So this should be like 900 Newton per meter. And so it's 0.9 Newton per millimeter. Newton per millimeter is a more common units. Any questions? One inch is 25.4 millimeters, just in case any of you still wondering. Okay. All right. If there's no question, let's do another one on torsional spring. This is a torsion spring. It's a different formula, obviously. The number of active coils is related to this length of the arm also. Okay, and then the spring rate formula like that. So let's just go ahead and do this one. So a stock spring displayed here. It's made from 1.8 millimeter diameter music wire again, right? So small d, that's the wire diameter. It has 4.5. So this is the body, and B is the body terms, because you have the arms, you have the legs, and then you have the body, right? So NB is 4.25 turns with straight torsion ends. It works over a pin of 10 diameter, 10 millimeter diameter. The coil outside diameter is the one we need. So the DO is 15 millimeters. And therefore, again, if you look at the body, what I want is the nominal diameter, which is the big diameter minus, so this is my D, and that is the outer diameter DO, right? So DO, so D is DO minus D over 2 minus D over 2, right? Because this is D. Okay? So this is 15 minus 1.8, 13.2 millimeters. We can look up, we also need the G later on. Do I have that table? The E, we need the E. So this is from table. We are 1.8 millimeters. What is that in inch? Now we go back and forth. Because this is in inch. 1.8 divided by 25.4 is 0.071. 0.071 inches. So we fall into this. This is the diameter range. Then E is 196.5 megapascal. Okay? Now, active turns, we need to first calculate the active turns. NA is equal to NB. I'll just write the numbers here. Oh, you already have it there. Nevertheless, I'll just write it. 4.25 plus, these are the lengths. What's it given? It's not given. L1 and L2 are these lengths.
Sir,
Yeah.
for the E, it's GPA or FMP?
It's the units, you mean?
Yeah.
Of, correct. Thank you. Where do they give the L? That's kind of magically appear.
We assume.
No. It works over a pin of the coil outside them to the pin. I mean, come on, the display is not really, I mean, it's not showing this is 10. Well, in my problem, it'll be well defined. Okay, so this is 3 pi d, which is the nominal diameter. So equivalent active is 4.65 turns. That's the active coil. Now, we're calculating the K. And the K is D to the 4th E. So this is L1 and L2. I'm just going to put question mark there because, I mean, it's not well defined there. Okay. So 10.8 D and A. Okay, now this is just math. Watch the units because we're doing all this in millimeters. Even though we did that conversion, that's only for looking up the table purposes. D is 13.2 times the active coil calculation. This is a torsional spring, so the unit is not Newton per millimeter, it's Newton millimeter because you multiply with torsion, right? Any questions? So you got the torque equals K times theta, right? So this is the calculation for the spring rate in relation to the spring geometry. That's going to be all that we're doing for springs. All right. That should be good for the day. We don't have time for motor sizing. We'll do motor sizing next week. Yes. Next week is it? We'll have one.
Will the makeup be in next week or?
Is next week the final week? No, I mean the 14th week.
No, next week is week 13.
Next week is week 13.
Next week
Okay.
13.
Yeah, I'll find the time. So we have motor sizing, and then I'll spend 1 week just to do a kind of a review of the quiz materials before the final exam. Okay, we'll spare 1 week for that. So we only have week 13 and 14 left, right? Yes. Week 13, we'll do motor sizing, and then week 14, let's do a quick quiz on springs and motor sizing, and then we'll do a review for the finals. Yeah. I don't think I have anything there, right? Do I have it in Google Classroom? I don't think so. Yeah, that's not that much. Now, when I do quiz review, I don't want to do it in front of you again. Like, that's kind of pointless because the quizzes are the same as the exercises we do. But I want you to ask the questions. Or maybe you can do it in front of the board, and then we'll discuss. I don't like to do reviews because it's just repeating, unless you ask the questions. But if you don't have any questions, then what to discuss, right?
Gerak mesin di sini udah pasti A. Enggak sih, kalau pakai